thank you so much for the introduction. So before dive into the auditory cortex, let me first introduce schizophrenia. So schizophrenia is a common and severe psychiatric disorder that affects nearly 1% of general population. But why I'm interested in that? Because auditory cortical dysfunction is widely observed in schizophrenia patients. So for example, auditory hallucination, which means the perception of a non-existing sound, is one of the typical symptoms of schizophrenia. And neurophysiology recording have shown that the auditory cortex have attenuated response to the different stimulus. And we also have seen that in the postmodern histology analysis that the auditory nervous circuits is altered in schizophrenia as well. And when we think about the causation of these kind of changes in the auditory cortex, we cannot ignore the fact that there's also a high prevalence of hearing loss in schizophrenia. So then we are meeting a more complex question that have genetic risk and also hearing loss. So in my project, we zoom onto a more fine question, is the temporal processing functions in schizophrenia. So here we're particularly interested in the gap detection thresholds, which means the shortest gap duration of a silent gap that one could notice in a continuous noise string. And we found that, and data have shown that there's abnormally elevated gap detection threshold in schizophrenia. And I think the audience here won't be surprised that hearing loss is self-elevated. So here we want to ask, do temporal processing deficits associated with hearing impairments and genetic risk factors for schizophrenia arise from the same mechanism, or actually there are different things, it's actually two different things. So then we choose this disease called 22q11.2 deletion syndrome. Nearly 25% of carriers could develop schizophrenia with this chromosome deletion, making it one of the strongest genetic risk factors. And also, among the carriers, more than half of them could develop hearing loss. The hearing loss is mainly conductive hearing loss that arises from chronic otitis media. So in my project, I use a homologous mouse model called DF1 mice, which have a very similar conductive hearing loss. And in the figure on the right here is showing the click evoke ABR. And this part of mice have hearing loss. So in my experiments, I first introducing conductive hearing loss in wild-type mice at P11 mouse pups. And then during development, I traced their hearing sensitivities using click evoke ABR again. So here the gray dashed line represents mice with malus removed, and the gray solid line represents mice with sham surgery. So based on the hearing sensitivity of wild-type mice, we then clustered DF1 mice into hearing loss and normal hearing groups. Then in the early adulthood, we performed in vivo electrophysiology using neuropixel probes. So here the mouse are head fixed and passive listen to gapping noise stimulus. So in every trial, there are two trains of noises, and the gap between two noises are separated from 0, which means no gap, to 256 milliseconds. Since the hearing of every mice is different, so here we adjusted the noise intensity levels based on the hearing sensitivities of each individual mice. So first, let's look at how a single neuron responds to a stimulus. So here I'm showing 3 example units, and you can see that there are a clear different responses either to the noise onset or to the noise offset. And if quantifying how all the neurons that we have recorded, we can see the majority of neurons still only responds to the sound onset. But of course, there's a neuron that have both response and only response to the offset. But we are more interested in how neuron response gradually changed with different gap durations. So here, each subplot is showing the PSTH of all neurons in that groups. And if we focus on the wild-type mice normal hearing groups at 4 milliseconds, we can already see that the neuron response differ due to the gap. However, in the DF1 hearing loss groups on the top here, the changes is quite minimal. So we then wonder how we can systematically quantifying the gap detection thresholds of single units. So to do that, we propose a method to use all the information in the peri gap window, which is shown in the blue box here. So the idea is that by calculating the deflections of neuron within gap window and comparing to the no gap condition, we can infer whether if the neural response changed due to the occurrence of a gap. And then we can measure how neural response, how the gap detection thresholds looks like in different mouse groups. So here we have seen that regardless of the genetic background, mice with hearing loss have the longest gap detection threshold as we have seen in the previous studies. But also we see that in DF1 normal hearing group, that is the orange line with orange solid line, there's also a mild elevation in the gap detection threshold here. Then we wonder if the data, the result we have seen in the single unit is preserved in the population, because we know that cortex function as a unit, as an entire unit. So then what we do here is we use principal components first to reduce dimensionalities of neural response. And then we can visualizing the population response as a trajectory in the principal component space. So here, with the increasing of the gap duration, we can see that the trajectory evoked by the second noise, which is shown in the dashed line here, is gradually emerged and getting more close to the trajectory evoked by the first stimulus. And by comparing the trajectory distance between these two noise, we can then infer how the dynamics of neural populations gradually changed at different gap conditions. But surprisingly, we only see the effects of the hearing loss, and which is quite interesting. And I'd like to discuss more about the differences between the single units and the population later in the poster session. So to quickly summarize, we have seen that both hearing loss and the deletions were associated with elevated gap detection thresholds in auditory cortical units, though the effects of hearing loss were more profound. However, in the neural population trajectory analysis, only hearing loss contributes significantly to the disruption of temporal processing acuity. In the end, I'd like to thank my lab members, my supervisor Jane, who is currently in London, and also our funding source. And also there are more posters from our labs coming this Thursday, so keep tuned on that. Thank you.
Are there any questions from the audience? Questions?
It's not an invited question. So what does this depletion do in the brain and somewhere else?
So it's a chromosome deletion that affects around like 40 genes that are expressed in the brain. So it has shown altered in the excitabilities of pyramidal neurons, and also there are like couple transcription factors also influence the receptor functions in the brain. So it's more like it's more than just like single genetic mutation. It's more like create a lot of alternations in the brain, and that's.
So is it specific to auditory cortex, or is it?
It's throughout the entire brain. Yeah.
So you don't know whether this actually derives from auditory cortex changes, or is it basically upstream?
So I think the hypothesis, our hypothesis, is that the chromosome deletion sets up like a more risky network that is more sensitive to the alternations of environment factors, and hearing loss itself become a risk factor that hits the system and driven these downstream abnormalities that we have seen.
Okay.
Yeah.
Thank you very much.